Welcome back to DeepVisus, where vision meets depth. I'm your host, and in today's episode, we're tackling one of the most profound questions in neuroscience and cognitive science. How does the seemingly continuous, fluid activity of our brains give rise to the discrete, decisive cognitive functions we experience every day, like making a choice, remembering a face, or focusing our attention? Our guide for this deep dive is Chapter 12, titled A Neural Approach to Cognition Based on Dynamic Field Theory, authored by Jonas and Gregor Schöner, from the insightful book Neural Fields Theory and Applications, published in 2014. This chapter aims to bridge a significant gap between the abstract mathematical models of neural activity and the concrete, observable behaviors of cognition. So, how does our brain's continuous, dynamic activity lead to these distinct cognitive functions? To begin to answer this, we first need to understand what we mean by neural fields. Imagine not just individual neurons firing in isolation, but rather vast, interconnected populations of neurons whose collective activity can be described as a continuous wave or pattern across a spatial area. These are mathematical models that capture the average activity of countless neurons over space and time, giving us a field of brain activity. Within these fields, information isn't coded by a single neuron, but by the collective. This is known as population coding. Think of it like a choir. No single singer carries the entire melody, but the combined voices create the full song. Similarly, in the brain, a specific sensory input or motor command activates a broad ensemble of neurons, each contributing to the overall representation. To analyze this, researchers use the distribution of population activation, or DPA, which is a method to visualize and interpret these collective activity patterns, showing how the shape of this activity landscape can reflect things like certainty or precision in our perception. Now, how do these neural fields behave? This is where dynamic field theory, or DFT, comes in. DFT is a theoretical framework that describes the evolution of these activation patterns over time. It uses a core mathematical model, often based on the Amari neural field equation, which includes factors like a resting level of activity, external sensory input, and crucial lateral interactions between different parts of the field. These interactions are often described by a Mexican hat shape, meaning nearby neural populations excite each other, while more distant ones inhibit each other. This balance of excitation and inhibition is key. DFT reveals that neural fields can settle into a set of stable states, which are like the brain's default modes for representing information. Sometimes input just creates a subthreshold peak, a weak input-driven bump of activity that doesn't lead to a strong decision. But if the input is strong enough, the field can undergo a detection instability, leading to a self-stabilized peak. This is a robust, localized bump of activity that sustains itself even with fluctuating input, representing a clear decision or the detection of a specific item. It's like the brain saying, "Yes, I see that." Crucially, these decisions exhibit hysteresis. This means that once a decision is made and a peak is formed, it takes a stronger change in input to make it disappear than it took to create it in the first place. This stickiness makes our perceptions and decisions stable and robust against noisy or fluctuating sensory information. Even more remarkably, DFT shows how self-sustained peaks can emerge. These are peaks that, once formed, can persist indefinitely even after the original input is removed. This is a fundamental mechanism for working memory, allowing us to hold information in mind without constantly perceiving it. DFT also provides mechanisms for handling multiple simultaneous inputs, which is critical in our complex world. A selection occurs when multiple inputs compete, and the field dynamics, often driven by a slight bias or noise, lead to one peak dominating and suppressing the others. This is how our brain might choose to focus on one sound in a noisy room. Conversely, if inputs are very close to each other, the field can exhibit fusion, where the individual inputs merge into a single averaged peak. Think of how our eyes might perceive a single, blended color if two very similar colors are presented close together. So, how does all this tie back to cognition? DFT argues that these dynamic properties, the ability to form stable peaks, to maintain them through self-sustenance, to exhibit hysteresis, and to perform selection or fusion, are the fundamental building blocks of cognitive processes. They allow the nervous system to generate and maintain internal states that are to a degree, independent from the immediate sensory environment, while still remaining flexible enough to be updated when truly relevant new information arrives. This balance between decoupling and coupling is at the heart of how we think and act. The chapter beautifully illustrates this with a detailed model of visual working memory and change detection. Imagine seeing a set of objects, then a brief delay, and then a second set. Your brain needs to remember the first set and compare it to the second to detect any changes. The DFT model uses a three-layer architecture: a perceptual field, which forms self-stabilized peaks for current input; a working memory field, which forms self-sustained peaks to hold information over time; and an inhibitory field that mediates their interaction. This model shows how a sustained memory peak can inhibit the perceptual field at its location, meaning a new input will only trigger a different response if it's sufficiently different from what's already in memory. It even explains phenomena like the limited capacity of working memory and how the proximity of items in memory can affect change detection. In conclusion, Chapter 12 provides a powerful answer to our initial question. It demonstrates that the continuous, dynamic activity of neural fields, through their inherent stable states and instabilities, can indeed give rise to discrete cognitive functions like decision-making, memory, and attention. DFT offers a neurally plausible framework for understanding how our brains achieve these remarkable feats, by elegantly balancing the need to isolate cognitive states from distractions with the capacity to link them to ongoing sensory and motor processes. This is just the beginning of understanding the incredible computational power of our brains. Join us next time on DeepVisus, as we continue to explore the intricate ways vision meets depth in the fascinating world of neuroscience. Stay tuned.